All right, welcome back to Unit 2, Notes 4, but this is going to be Part 2. In Part 1, we talked about the metals on the periodic table, but here in Part 2, we're going to be talking about the nonmetals. The nonmetals are located on the far right of the periodic table. They make up like 1/3 of all the elements. So we talked about the metals before and their properties. Hopefully we get a good understanding of what those look like and of what properties they have. But today, we're going to be discussing the nonmetals, what they're used for, and some of their properties. To start off, some of the properties of nonmetals. Most of them are going to be gases at room temperature, which means they typically have a low melting and boiling point. All right, so the boiling point probably going to be like in the negative tens or hundreds of degrees Celsius. So it's really, really cold. If you think about, like, for instance, liquid nitrogen, you might have seen like a science experiment of someone having liquid nitrogen. It's extremely cold to have a liquid nitrogen, and it just kind of evaporates at a very, very low temperature, or boils. Actually, it doesn't evaporate; it boils. Same thing with for instance, a compound known as dry ice. It's basically a solid version of carbon dioxide. That's all it is. Dry ice is a solidified carbon dioxide. But again, it's extremely cold, and you have to keep it that cold in order to have it at a solid state. Okay. Other nonmetals that are not gases can be found as solids. So there are nonmetals that can be found as solids. But unlike metals, metals are very rigid and tough, and like you have to put in a lot of mechanical effort to break it apart. Not so with nonmetals. With nonmetals, if you find them as a solid, they're very brittle and they're very easy to break apart. Another property of nonmetals is that they don't conduct electricity very well. Not like metals. Metals can conduct electricity very well, so they are really good insulators. So we use a lot of nonmetals, and we use compounds derived from nonmetals to insulate from electricity. Likewise, we also use it to insulate from heat. So, like, for instance, silicone is a material that's made out of primarily the element silicon, and that is used as an insulator. Okay, you might have heard of the term Silicon Valley, which can be found, of course, in California. The reason why they call it Silicon Valley, because in that part of the world, in that part of the country, they make a lot of electronic devices, a lot of our gadgets and whatnot. And so they use what's called PCB boards. And PCB boards are like these green boards over here with wires going in between. And one of the main elements in PCB boards is silicon. And silicon is a really good insulator. And so you typically have copper wire and a silicon-based board to kind of control where electricity goes. All right. So nonmetals, they don't conduct electricity, but they also don't conduct heat. All right. So just keep that in mind. They are also really important elements because they make up most of the mass of living organisms. So roughly 99% or more of our elements in our body can be found as these elements. Oxygen is a nonmetal, carbon is a nonmetal, hydrogen, nitrogen, those are all nonmetals. Of course, calcium here is a metal, it's an alkaline earth metal, but it is the most abundant metal in the body. A lot of people think it's iron because you have iron in your blood, but actually it's calcium because calcium can be found in your bones. And so your bones have a lot more mass than your blood, and so you have a lot more calcium. But you can take a look. If you just found all of the elements in the human body, 65% of it is oxygen, which is kind of crazy to think about. And then a lot of it is hydrogen and carbon as well. So close to 90% is just those three elements, and then you have a little bit of some other ones as well. So nonmetals do make up the mass of living things, and without the nonmetals, you wouldn't necessarily have life. To talk about the most important nonmetal, though, it's probably hydrogen. Hydrogen exists as H2 when alone as an element, so it's known as diatomic. And we'll talk a little bit more about that in a little bit, what the term diatomic means. But basically, di means di, that means two. Atomic means atom, so it's diatomic. And again, I'll go into more detail about this in a little bit. But whenever we see hydrogen, basically what that means is that hydrogen is never by itself. It's always paired with another hydrogen. So we always write it as H2. Okay? It is also the most abundant element in the entire universe. All of the universe, if you take every single atom of the universe and you are somehow able to gather them all into one space, 90% of all of the atoms in the universe are hydrogen, which is kind of crazy to think about. So that's why it's one of the most important elements. You can also do a lot of reactions with hydrogen. It's the simplest one. It's a simple proton. That's all it is. So it's got a mass of 1, meaning that it has typically no neutrons. You can have hydrogen that has neutrons, but those isotopes are pretty rare. So for the most part, hydrogen exists as just a single proton. And we're going to watch a little quick video of hydrogen and what happens when you mix hydrogen with oxygen. So to explain exactly what's happening before we play this video, we've got 3 different balloons. We've got hydrogen, we've got oxygen, and we have a mixture of hydrogen plus oxygen. Okay, so hydrogen by itself, it is technically a flammable gas because we have a lot of oxygen in our atmosphere, but it's not that flammable. Oxygen is pretty flammable, like it could burn oxygen at a very high temperature. And then this last balloon is going to be a mixture of hydrogen and oxygen, and it's just going to show you exactly what happens when you apply a flame to it. So let's go ahead and play this video. All right, so obviously the yellow balloon produced the biggest explosion. And so when hydrogen and oxygen mix, that can perform a very violent reaction in which you have a combustion. And the byproduct of this combustion is actually water vapor. So fortunately, we can utilize the properties of hydrogen and mixing it with oxygen to kind of create vehicles that run on hydrogen gas. And we can kind of contain this explosion inside of an engine. And so you can have vehicles that run on hydrogen, and then you can just have water vapor be your only byproduct that comes out. There's no carbon dioxide, no harmful chemicals. It's just water vapor that is produced from this reaction. This reaction is also well known in the movie The Martian. I think I've mentioned this before, but in The Martian, he makes water using hydrogen and oxygen in his little capsule or wherever he's staying.
The problem is water. I have created 126 square meters of soil, but every cubic meter of soil requires 40 liters of water to be farmable. So I gotta make a lot more water. Good thing is I know the recipe. You take hydrogen, you add oxygen, you burn. Now I have hundreds of liters of unused hydrazine at the NDB. If I run the hydrazine over an iridium catalyst, it'll separate into N2 and H2. And then if I just direct the hydrogen into a small area and burn it.
Unfortunately, there are, of course, historical instances in which hydrogen and oxygen mixing can lead to catastrophic failures like this, what you see on the screen. This is known as the Hindenburg incident of, I believe, 1937, 36 or 37. And the Hindenburg was a Zeppelin, and a Zeppelin is kind of like a blimp. And for a long time, this was kind of like the main means of transportation across the Atlantic Ocean, going from Europe to America and back forth. Also, some trips to South America as well. You would travel in this giant balloon, basically, and it would go pretty slowly. It would take a few days to travel from Europe to America. I think it would take about 3 days or so. So this Zeppelin company basically left Frankfurt, Germany back in 1937, about 100 people on board, and they were making their way to New Jersey. And right as they were kind of mooring and kind of docking the Zeppelin, the outer coating of the Zeppelin was coated in like this very thin metallic film, kind of for durability's sake, but also just kind of part of the design. Well, that metallic surface came in contact with some electrical wires, and when you make contact with electricity with metal, you know that sparks can fly, and the sparks ignited the hydrogen inside of this giant zeppelin, this giant balloon, and when it mixed with the atmospheric oxygen, this entire thing just kind of combusted and blew up, and it slowly burned. The outer coating, the metallic surface of the zeppelin was actually very flammable, so it burned, and the whole thing crashed to the ground. I believe there were about 36 fatalities, maybe 37, something like that. I think 36 out of the close to 100 people. So there were several survivors of this incident, despite how tragic it was. And it's one of the first tragedies that has been captured on film, and I believe you can find videos of this on YouTube somewhere. Moving on, however, we're going to talk about the families of the periodic table, the non-metals specifically. They actually do have names, and we're going to follow the same rules that we followed with the metals, with the valence electrons and things like that. We're going to start with the far right and move our way inwards. So the group 8 over here, this group has 8 valence electrons. That is called the noble gases. And they're found in group 18 or 8A, depending what version of the periodic table you're looking at. And all of these, except for one, all of these have 8 valence electrons. And I said except for one because the one that doesn't have 8 valence electrons is this guy up here. This is helium. Sorry, not neon. Neon's below. Helium is the one that has only 2 valence electrons. And the reason why it only has 2 valence electrons is because it's element number 2. So it can't physically fit 8 valence electrons. So the rest of them do have 8 valence electrons. And if you remember what I talked about a little bit in the metallic section in part 1 of notes 4, elements that have 8 valence electrons are very comfortable. And so this section of the periodic table does not react with anything. It's very hard for some of these to get into a reaction. Some of them can do reactions, but most of them don't do any reactions whatsoever, and they just kind of remain stable by themselves. Hence why you can take like gases like helium and breathe it into your lungs, and then it doesn't do anything. It just kind of sits there, and you can do that squeaky voice trick, I guess. But it doesn't react with anything in your lungs, so it's typically safe, minus the fact that you're kind of slowly suffocating yourself because you're depriving yourself of oxygen. But for the most part, it's safe to inhale helium. All right. So like I mentioned before, all of these have 8 valence electrons. If you take a look at the energy levels here, I'm going to go ahead and kind of move myself aside. 1 second. There we go. Or I'll just disable it. There we go. 2 plus 2 valence electrons in this energy level plus another 6 gives us 8. And the third energy level, we have 2 and then another 6, 8. Fourth energy level, same thing. 2 and 6 makes 8, so on and so forth. What we notice, though, is that helium has only 2 valence electrons. Okay, so that's the key thing we want to make a note of. They all have energy levels full of electrons except for helium, like I mentioned, and they exist only as elements in nature, no compounds. They are chemically inert. So what does inert mean? It means that it doesn't do any sort of reactions, no reactions whatsoever. All right, so if we can't do any reactions with the noble gases, what do we do with all of them? Funny enough, helium is used for balloons a lot of the time. Argon is found in our atmosphere. We don't really use it too much. It's one of the most abundant gases in our atmosphere besides oxygen and nitrogen and all of that. Argon is the most abundant noble gas. And so we're constantly breathing in argon with no issues. But what do we use it for? Oftentimes we use it for lighting and for insulation purposes. For instance, windows. So if you take a look at windows nowadays, modern windows have 2, sometimes even 3 panes of glass. So it's just like glass, glass, and then another sheet of glass typically. And it's not air in between the panes of glass. It's a gas called argon, the yellow one here that you see. Argon is filled in between the panes of glass, and it's sealed in there so it can't escape. And the reason for that is because in Minnesota especially, we have like really cold winters. And so we want to insulate from the windows so we don't lose a lot of heat from the inside or bring in a lot of the cold air. And so we insulate our windows with several panes, and in between is that gas that cannot transfer heat between the panes of glass that well. And so we use argon or other noble gases to kind of insulate our windows. All right. Some of these are heavier and denser than air. Argon is about the same density as air, but it's just like slightly. Krypton and xenon are much heavier than air. Helium and neon are lighter. Helium, of course, being the lightest of the noble gases, and that's why we fill up balloons with helium. And so that, I guess, one of the other reasons why we use helium is to fill up balloons, because it floats. All right, so we're going to take a little video break, and we're going to take a look at this video of how these noble gases differ in density and weight.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
Next up on the periodic table, group 7, or sometimes group 17, these are known as the halogens, okay? And unlike group 8, which doesn't react at all, group 7, the halogens, are some of the most reactive elements. So it's funny that it's right next to each other. And the reason for that is because of that valence electron rule that we were talking about, how elements like to be comfortable with 8 valence electrons. Well, you can kind of predict from our pattern that elements in group 7A or 17 have 7 valence electrons. So they're missing only 1 valence electron to kind of be comfortable or kind of be in a stable state. And so because of that, they're very reactive looking for that last electron. Okay, so all of these have 7 valence electrons, and you can take a look at all of these different elements: fluorine, chlorine, bromine, so on and so forth. They all have 7 valence electrons in their last energy level. For fluorine, in the second energy level, we have 2 and then 5. For chlorine, we have 2 of 5 again. For bromine, we have 2 and 5 again. The only difference is, of course, the energy level. Okay, and so it kind of looks even funny. Like if we take a look at fluorine, for instance, it just looks kind of funny. The outer shell is not really filled out. It looks asymmetrical, and so it's looking for that last valence electron to kind of fill that outer shell and make it a little bit more stable. Therefore, they react really easily with group 1 on the periodic table, the alkali metals. Alkali metals have 1 extra valence electron, and so they're very willing to give up that 1 extra valence electron. And so when they do give it up, they're going to give it up oftentimes to halogens, because halogens are very willing to accept that 1 valence electron. So these are also going to be the most reactive nonmetals. Fluorine by far being the most reactive, chlorine, bromine, so on and so forth. Okay? These also exist as diatomic molecules when alone as elements. And like I mentioned before, I'll talk about what it means to be diatomic, but basically they exist only in pairs. So bromine cannot be Br by itself. When it's just by itself as a gas, for instance, like this is bromine gas over here, it's going to be listed as Br2. Same thing with fluorine and chlorine and all of these different halogens. They are always listed as diatomic, so they have 2. So F2, Cl2, Br2, I2, so on and so forth. And the more intense halogens are closer to the top, like I mentioned before. Fluorine is the most reactive out of all of them. It's more reactive than chlorine. Chlorine's still pretty reactive though, but it's more reactive than bromine, and bromine's more reactive than iodine, and so on and so forth. Fluorine's really reactive. Typically, chemists will be the only people that use fluorine only when they have to. Chlorine is found in very small concentrations in like Sometimes in drinking water we have chloride. Sometimes we use it in swimming pools. We add just a little bit of chlorine to keep it sanitary, so we don't have like algae growing or bacteria or anything like that in pools. Bromine, not very reactive. And then finally iodine. That's like one of the first ones that's kind of safe to use on the human body. Sometimes before a surgery, a doctor will like cover a part that's being affected. Like if, let's say I'm getting surgery on my hand, and they would cover my hand with like this yellow liquid, and it dyes my skin. Well, that yellow liquid is iodine, and it's basically sterilizing my skin. It's eliminating all pathogens, all sorts of bacteria or viruses that could be living on my skin. That iodine is reacting with that to make sure I don't get an infection. You could also use iodine if you're like going camping. A lot of people bring iodine tablets if you plan on drinking fresh water that's out in the open. Like if you fill up a water bottle in a lake or a stream, there might be things living in that water, even though it's fresh water. And if you don't filter it out, what you could also do is just put in a few iodine tablets in the water, shake up the water bottle, wait about 30 minutes or so for the iodine to dissolve and to kill anything that might be in that water, and then you could drink it. It's not a good idea to do that like all the time, but if you're just going camping, it's a perfectly reasonable method of disinfecting the water. Now, I did have a couple of videos I wanted to show you. The first video was an apple versus hydrochloric acid, which is the same type of acid that we find in our stomachs, and it helps digest food. And the other one is hydrofluoric acid, and hydrofluoric acid is more powerful than hydrochloric acid for the same reason that fluorine is more powerful than chlorine. Unfortunately, though, some of the videos have been taken down. I guess the users on YouTube, their accounts got deleted, or they just simply removed the videos, but they're no longer there. But I did find another video that I want to show you, showing the reactivity of the halogens and how they react differently. So we're going to go ahead and watch that now.
Here are the 4 halogen elements: fluorine, chlorine, bromine, and iodine. Fluorine on the left is almost colorless. Next comes chlorine, which is greenish yellow. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid and iodine is a solid. Even so, they're both quite volatile. You can see the colored vapors, orange-red above the liquid bromine and purple above the solid iodine. Whether solid, liquid or gas, the halogen elements consist of diatomic molecules, F2, Cl2, Br2 and I2. Fluorine reacts often ferociously with almost everything else. A stream of fluorine instantly sets iron wool on fire, and it does the same thing to charcoal. Now let's see the reaction with hydrogen. There's hydrogen in the balloon. A jet of fluorine gas pierces the balloon and explodes with the hydrogen inside. Let's see it again in slow motion. Now you can see the fireball more clearly. Now the reaction between hydrogen and chlorine. I light the hydrogen at the jet and lower it into a jar of chlorine. The hydrogen carries on burning, but with a pale blue flame. When the halogens react with hydrogen, the hydrogen halides are produced: HF, HCl, HBr and HI. In each compound, the halogen has a valency of 1. All 4 compounds are gases. They're also very soluble in water. Here's water swallowing a jar of hydrogen chloride. Now let's see how the halogens react with aluminium. When aluminium powder meets fluorine gas, the reaction's over in a flash. To get chlorine to react with aluminium, I'll heat some foil in a stream of the gas. The white fumes are aluminium trichloride. With bromine, I just drop aluminium foil into the liquid. There's a short delay, but normal service is soon resumed. Once the reaction gets going, it quickly takes on the appearance of the pit of hell. As with the chlorine reaction, there's white smoke. That's aluminium tribromide. The reaction with iodine is just as spectacular. A little warming helps to get things moving, but once the reaction's off, it needs no further assistance.
All right, so now that we've talked about the halogens, the next set of groups that we're going to talk about are called the mixed groups. And the mixed groups are called so it's because the columns in which they're in have a mixture of both metals, nonmetals, and a new category called metalloids. I've mentioned metalloids before. The metalloids are going to be these green ones that you see on the periodic table, kind of like forming the staircase. And basically they have properties of both metals and nonmetals. Okay, so the mixed groups, they are named after the element that's actually at the top of the group. So for example, we have group 13 is the boron group because boron is going to be the element that's on top. So if we go back to this periodic table, here's boron. This entire column is called the boron group. This group over here is called the carbon group. This group is called the nitrogen group, and you could probably guess this group over here is called the oxygen group. So very simple naming. We would just call them by what the element on top is. Okay, so in the mixed groups we have these things called metalloids, and like I mentioned before, they have properties of both metals and nonmetals. They are sometimes called semi-metals, but most people just call them metalloids, and they kind of form like this staircase pattern. Starting with boron at the top and going all the way down to polonium. And if we follow the staircase pattern, there's actually one step that's missing right here, and there's supposed to be an element right here. That element is aluminum, but aluminum is not a metalloid. Aluminum is indeed a metal, so aluminum does not follow the same pattern of the metalloids. So just keep that in mind, I guess. That'll be helpful for when we do a lab later, that this element right here is not a metalloid. Okay. Next up is a term we haven't talked about yet. It's allotropes, and allotropes are basically when we have an element that can exist in multiple different forms, when we have a lot of it. Okay, so for example, we have two different allotropes of carbon present here on the screen. The most common example of carbon that we deal with pretty much on a daily basis here at school is pencil lead. Now, pencil lead is not actually lead. Lead is another element, but we don't use lead because lead is toxic. So we use what's called graphite, and graphite is made out of carbon. And so if we take carbon and we arrange the atoms to be like in hexagons like this, and then we arrange the hexagons into sheets, you can kind of see that it forms like this carbon. But instead of taking the hexagons and forming into sheets, we kind of form like these geometric shapes. We can actually rearrange the carbon to form diamonds. Okay, so these are two different allotropes of carbon. Both of these substances are carbon. We've got the graphite over here and we've got the diamonds over here. They're both made out of the exact same element. They just exist in different forms. Okay, taking a different look at it, the diamond structure is going to be three-dimensional, whereas the graphite structure is going to be mostly two-dimensional. It's going to be kind of like stacked together in sheets or in layers. So diamonds are actually like really, really hard substances. It's the hardest substance on the planet. There's nothing harder than a diamond due to its rigidity and the crystalline structure that carbon can actually form here. And graphite is actually fairly weak in comparison to a lot of things. Graphite is used to even just like scratch onto paper. The paper itself is harder than the graphite, hence why you can scratch the graphite onto the paper. Okay. However, you can make another allotrope of carbon, and there's a new material called graphene, and it basically is sheets of bonded carbon atoms that is similar to graphite. So you take these hexagons and you form these very large sheets, and then you kind of stack them together. And graphene is very, very thin. It is one atom thick. So you have this entire sheet that is one atom thick, and you could take multiple sheets and kind of stack them together. And it's very, very strong. It's like 100 times stronger than steel. So if you think of like carbon fiber is very similar to this, where the material is very, very light, but it's also very, very strong. Okay, so for instance, we have a bike frame that is made out of graphene, and it weighs just 750 grams. And for reference, that's 1.7 pounds. That's very light. A similar bike frame that is made out of, let's say, aluminum is much heavier than this. It's going to be closer to like 5 pounds or even up to 10 pounds if it's made out of steel. But similar bike frames can actually be made out of graphene if we conserve on material to weigh less than 1 pound, which is if you are, a competitive cyclist, that might be something that would give you a huge advantage over your opponents, where you don't have to bike with so much weight. Your bike actually weighs a lot less. And the rigidity is still there. So the material is quite fascinating because it's strong, but it's also very lightweight. So I've been throwing around this word diatomic throughout the lecture today, and I think it's finally time that we talk about what diatomic means. Diatomic, if we break up the word again, the first part, the di, means two. Atomic means atom, so it basically means two atoms. And so diatomic elements are elements that exist in pairs. You can never find just one atom of these elements. They're always going to be paired up, and that's because of their valence electrons and how unstable they are. And so when they have like another element next to them, that helps them stabilize the element so that it's not going to be as reactive. Okay, so diatomic elements, just as a review, are elements that almost never exist in a one atom state. Okay, and what elements are there? Fortunately, there's not too many of them, and there's only 7 diatomic elements. And how to remember them, this is the way I was taught when I took chemistry in high school. It's Brinkelhoff. That's the acronym that we're going to come up with. And some of these letters are capitalized and some of them are not. That's to indicate which of these elements are diatomic. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine are all diatomic. Okay, so they are always written as Br2, I2, whatever. They always have a 2 at the end when it's just that element. Okay, now, however, you can mix these elements with other elements and form compounds, and they do not have to be diatomic. So, for example, we have H2O, right? So that's water. We know what water is. H2O does not mean that the O has to be diatomic. And the hydrogens are not actually attached to each other. We have 2 hydrogens on the sides with 1 oxygen in the middle, and the 2 hydrogens are connected to the oxygen. So just to reiterate, when these elements are by themselves, they will always be diatomic. They will always exist in pairs. But that's not always the case when they react with other elements. All right, so on the periodic table, where are all of these elements found? Well, we call them like kind of the super 7. And I remember that because you can create like almost, you can imagine this is the number 7 on the periodic table. So we start with nitrogen and we go to fluorine. And it's basically these 4 halogens, a lot of the halogens, then nitrogen and oxygen, and then we have hydrogen over here. Those are going to be the 7 diatomic elements. And just to recap why they are diatomic, it's got to do with their valence electrons. So for instance, let's take a look at this. If bromine has 7 valence electrons, what would the bonds look like in a diatomic atom? So I'm going to walk through this with you. We've got 2 bromines, and I've color-coded them to kind of help visualize what's going on here. We've got a red one, and we've got a blue one. The red electrons around the red bromine means that it belongs only to that bromine, and the blue ones mean that it only belongs to that blue bromine. However, the purple ones in the middle can be shared in between. And if we remember, we talked about how an atom that has 8 valence electrons is stable. We can see that this bromine, if we're sharing these 2, this bromine technically has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Same thing with this bromine, 1, 2, 3, 4, 5, 6, 7, 8. And so since they're both willing to share an electron, they're forming a bond, and that's what makes them diatomic. They're forming that bond because they're both willing to share an electron, helping them be stable. Okay? And so if iodine has 7 valence electrons, what would the bonds look like? It's kind of like the same thing that bromine had. We have these 2 shared in the middle. So iodine has all of these 8, and this other iodine has these 8. And so we're stabilizing both of these atoms with the valence electrons. All right, nitrogen has only 5 valence electrons. So if we wanted to pair them up, this is what it would look like. The nitrogen has 1, 2, 3, 4, 5, and this nitrogen has 1, 2, 3, 4, 5. But they're both willing to share 3 electrons each. So over here we've got 6, and then we have 2, and then 2. So this nitrogen technically has access to these 8, and this nitrogen has access to these 8. All right. Chlorine has 7 valence electrons, so it looks very similar to bromine and iodine. Same thing with fluorine. We'll see that in a minute. Hydrogen has 1 valence electron, so what does that look like? Well, there are some instances, very few instances, where an atom is actually stable if it only has 2 valence electrons. So there's only a few atoms that can do that, like hydrogen, helium, and lithium and magnesium are the only ones that can be stable with only 2 valence electrons. And that's just because they're so small, they can't actually fit 8 valence electrons. So this hydrogen has 1, and this other hydrogen has 1, but if they're stable with 2, they only have to share 1 each, and then they can become stable if they pair up. Oxygen has 6 valence electrons, so what would that look like? Well, we have 1, 2, 3, 4, 5, 6 for this oxygen, and then another 6 for this oxygen, but they're both willing to share 2. So now this oxygen has access to 8, and this oxygen has access to 8. And finally, fluorine does the same thing, where we see with the other halogens, they are both willing to share 1, and they form a bond. Now, this is actually going to transition us to our next unit, Unit 3, where we start actually taking elements and we're combining them together, looking at the valence electrons and creating different types of reactions with different elements. So this is actually kind of like a preview of what we're going to witness in the next unit. All right, so what I would like for you to do now is to take a look at notes 4 and practice problems 6 through 10 will be just like a comprehensive review of all the material that we've been talking about. So take a few minutes, maybe 5 to 10 minutes or so to work on this, and we will check the answers with a follow-up video posted in the module.